All right, guys. Hey, welcome back to another lesson. Today we're going to talk about matrices and operations with matrices. Um, Matrices pretty much can represent a bunch of different things. It could represent what's called a vector. Okay, a vector is just a line with some sort of direction to it. Okay, not a full line, half a line. Matrices can also represent a system of equations, which we know is coming from planes, where planes intersect. Okay, so there are a lot of great useful applications to this. This is pretty much the whole topic of linear algebra. So if you in college end up taking linear algebra, this is something that you'll dabble into. A lot of good applications to this. It's becoming more and more of a birthplace of so many different things with mathematics nowadays. Matrices are seen a lot of different places, and I think it's become a lot more and more popular with it too. So this is actually really cool. I can't wait to show you some stuff here. So let's go ahead and talk about what is a matrix. So a matrix is just an array of numbers, okay? And it's organized in these nice little brackets. The brackets can be like these big, large parentheses, or you can make them square like this, either way, okay? So right here is an example of a matrix down here below. So there's all my numbers being organized, okay, in this nice little list. When you organize a matrix, okay, we'll talk about what's called size, okay? How big is this matrix of numbers? All right, well, if I look at it, it has 3 rows, this one in particular, and it has 3 columns. So I would call this a 3 by 3 matrix, okay? So this would be the dimension. I can't spell. Help me, help me. Okay, dimension, or in other words, the size of the matrix. Now you're probably wondering, okay, what number represents what? The first number is always going to be the rows, the number of rows a matrix has. The second number is going to be the columns, the number of columns a matrix has. So at any time when you're trying to figure out what are the dimensions, how big is the matrix, you go by how many rows and by how many columns. So it's a 3 by 3 for this guy, okay? Now you're probably wondering, well, Mr. McCullough, you kind of avoided this top part. What does this top part mean? Okay, well, the top part is telling you the positions, okay? Now, A is just an arbitrary variable that they put in there. They're just calling this, this is A, 3, 1, or A, row 3, column 1. So these are telling you the positions, okay? Because let's think of it this way. Let's say I'm looking at this matrix, and I want to figure out specifically what number I'm looking at. And to describe it to someone could be difficult, especially if the matrix is large. Think of a 100 by 100 matrix. That's a huge matrix. So you want to come up with a way to pinpoint what location you're looking at. So here's what it is. Just like this, row by column, okay? If I look at this first position, element, and these are called elements, by the way. Sorry. So the first element would be in the A11 position, row 1, column 1. If I go to 4, 4 is in the row 2 position, column 1. Okay, remember, it's always row by column. If you keep that in your mind, the rest of this becomes a lot easier. And then for the 7, that element is located in row 3, column 1. Okay, so here's row 1, row 2, row 3, column 1. So we can go over here. This guy, okay, is going to be row 2, column 3. Row 1, row 2, 1, 2, 3. Boom, there it is. Okay? So the first number is what row is the element in. The second number is what column it's in. Okay? So that's just what a matrix is. It's just an array of numbers. It can represent anything. Okay? And we'll get into what those representations are right now. Let's say I have this matrix. And let's say that this is the information of tuition, room and board, and enrollment for 3 different universities, ISU, UI, and UNI. Okay? And I wrote this down because I knew this was going to happen. UNI is University of Northern Iowa. ISU is Illinois University, and UI is University of Iowa. Okay, I looked it up. I'm still going to probably get people on the internet saying, no, it's actually this. I apologize, okay? So each row in this matrix represents the university. Each column represents tuition. Column 2 is room and board, and column 3 is enrollment. Okay, so you see how this matrix kind of works out here. So if you look, if I look at this position, okay, the University of, this is Iowa, this number represents the amount of money for room and board, $7,250 for this university. If I want to know, let's see, this is what, University of Northern Iowa, this college, if I go over here, this number represents what, the number of people enrolled, which would be 12,609 students. Okay, so hopefully you can see just how to work with those numbers. Okay, let's go ahead and look at the problem. It says find the average of elements in column 1 and interpret the result. Okay, so let's go ahead and do that. Let's see. So the average is you add up the numbers and you divide it by how many data points there are. Okay. So column 1's here. So I'm going to add up all those guys together. So we're going to take the average of column 1. Okay. So we're going to add up. That symbol is a summation symbol, and I drew that poorly. I have a hard time drawing those. So that just means add up. Add up everything that's here in column 1 and divide it by the number of items. Okay, or in this case, what? Rows, how many rows we have. So that's going to be what? 6,160, 6,293, 5,352 divided by 3. Okay. When you do this, the average comes out to be $5,935. So this is the average for column 1. If I add them up, divide by 3, that's the average. Now let's interpret the result. What does that mean? Well, the first column represents tuition. So we just found the average tuition for all 3 of these universities. Okay? That's what that is. So I'll write that down over here. So it's the average for all 3 colleges. Colleges, universities, however you want to say it. I'm going to pick a different, I don't want that to run out. Okay. Next question. Same matrix. Which university's total cost is the lowest? Okay. So how am I going to figure out that guy? Well, I think it's going to be what? 2 columns I'm looking at. Column 1 and column 2 are costs, right? This is your tuition. This is room and board. This guy over here is enrollment. That's people. Okay, I'm not going to do that. So what I'm going to do is I'm going to take each college and I'm going to add up both their totals, right? I'm going to add up their total in column 1 and column 2. So ISU's total is going to be 6,160 plus 5,958. UI would be 6,293, 7,250, and UNI would be 5,352, 6,280. Now remember, these numbers represent tuition. This is room and board. So if I add up all their totals, I get 12,118, 13,543, and the last total is 11,632. So if I'm comparing colleges, and these are the 3 I'm looking for, it looks like this guy, University of Northern Iowa, has the cheapest cost per year. Okay. See how we're just using different positions of the matrix to figure out these things? Okay. All right. Last one, and then we'll go into some other operations. Would adding the elements of the rows provide meaningful data? So what that means is if I add this row to row 2 to row 3, if I add them all together, does that give me anything that's meaningful? Okay, do I get anything from it? Okay. And the answer would be what? No, it really wouldn't. It's not giving us anything useful. If I add all 3 tuitions, I get the total cost from all 3, but that's not going to help my decision. That gives me all room and board, and this gives me the total enrollment for all 3 universities. So it's not really giving me anything additional. Unlike the first question, which was, what's the average of column 1? That gives me the average of all three of these. So that could provide me a little bit of information like, okay, on average, this is how much I'm spending at these 3. Is this below or above the average? And you can make some comparisons. And the other thing is, too, the first 2 columns, we're talking about cost. The last column is enrollment. So even if we were to add the elements going column-wise, it wouldn't make any sense because you're combining cost and total. So when it comes to a matrix, you can kind of see where the position of the number is important. I can't just start adding this number to this number. It doesn't make sense in terms of context here. So the position of each element in this matrix is very important. Okay? That's what I want to get across to you guys. It's very important. Now, I do have other questions here. It's in my notes, so you can kind of see what they are in the future. You can look at those ahead of time, if you'd like. Alrighty. So, let's take a look at this. Adding and subtracting matrices. So, going back to that last point I emphasized, each element in its position is important. Okay? It has context somehow, some way. So I can't just add them randomly. Okay? So if we take a look here, if I'm adding 2 matrices, plural, together, I need to add them based on their position. So in this little example here, A and E, they're both in the 1, 1 position, so I'm going to add them together. Okay? I'm not going to add A to G because their positions are not the same. B and F, I will add those 2 guys together because they're in the row 1, column 2 position. And then C, D, and GH, I would add them respectively to their positions as well. Okay, so it's very important. Even with subtraction, you want to make sure you're subtracting them based on their positions. Okay. Now, if you look at this, what happens when one matrix is bigger than another one? Can you really add them together? And the answer is no, because the positions aren't going to match up. Okay. If I go back to the first example, I'm not going to add that matrix of 3 colleges to another matrix of 5 colleges. One's going to have more elements than the other, so it doesn't make sense to add those guys together. It won't come out right because the dimensions are not the same. So, in other words, when you're adding or subtracting, you want to make sure the dimensions are the same. Okay? So here's the first one. So I'm going to add these 2 together. And the markers are squeaking. Squeaking markers. Okay, so we're going to add matrix A and matrix B together. Okay. Now notice this is a 2 by 2 matrix. 2 rows, 2 columns. This is another 2 by 2 matrix. So because they're the same, I can add them, and it also means the result I get is going to be a 2 by 2 matrix. So now let's add them based on their positions. So 6 and -3 will be added together. They're in the 1, 1 position. So I get 3. 4 and 1 are in the same position. They get 5 when I add them. -1 and 0 will give me -1. 0 plus 3 gives me 3. So here's my new matrix. That'll be my answer for that guy. Okay. Now, if you're completely foreign to this, you might guess how to add these already on their locations. Okay. But I'm just hoping that first example kind of helps it along here. All right, next example. We have matrix A and matrix B. Now, notice something here. I'm going to rewrite it over here. And we're going to subtract them. Okay. The size of this guy is a 2 by 3, 2 rows, 3 columns. This guy's a 2 by 2. See how the dimensions don't match? So in this case, cannot be done. dimensions don't match. Because here's the deal. I can add these two together because they're in the 1, 1 position. I can add these two together because they're in the 1, 2 position. But this 0, I have nothing to add to it, right? This 0 is in the 1, 3 position. I can't add anything there. Same thing with this negative 1. There's nothing. It's like there's a ghost column that doesn't exist. These guys aren't being added to, or subtracted, I'm sorry. They're not being subtracted. So in that case, I can't do this, okay? So think of it this way. This matrix represents something different than this guy then. It's like the two topics don't mix. Okay? So the last one, and you can probably see the answer for this guy. I have these two matrices. If I add them together, what's the answer going to be? Well, the answer is going to be the last one, right? Their dimensions are different. The matrices cannot be added. That's a 2 by 2. This guy is a what? 2 by 3. They have to match up. Okay. Next, and I'm trying to make this as small as possible, this video. Multiplying by a scalar. Okay, a scalar is a number that's in front of a matrix. Okay, and so for instance, like if this was a k value here, we're multiplying by this whole matrix. Every element gets multiplied by that scalar. Okay, so if you look at the example here, if I had a negative 3 that's outside this matrix, I'd multiply every element by negative 3. Okay, that's what a scalar does. So let's take a look at this guy. So we're out of the realm of addition, subtraction, which I think that's a pretty simple operation, given that we know how to do it now. So I'm going to figure out what 2 times this matrix will equal. Okay. Now, notice if I multiply by a scalar, it doesn't matter what size the dimension is. Okay. So it's going to be the same dimension. This is a what? A 3 by 2? 3 rows by 2 columns. So this will still be a 3 by 2. This scalar does not make the matrix bigger. All right? It's only making the elements side of it bigger or smaller depending on what the scalar number is. So 2 times 2 is 4. 2 times negative 1 is negative 2. 0 times 2 is 0. 2 times 1 is 2. 2 times 3 is 6. 2 times 5 is 10. There's my final answer for that guy. That's what it would represent. Okay? All right, let's do another one. So let's do 4 times this matrix. Now they're calling these matrix A. Honestly, you can name a matrix anything you like. You really can. So this is a 2 by 3, which means my answer is still going to be a 2 by 3. It doesn't change. This 4 out in front means I'm going to multiply everything by 4. So this first element's 8, 12, and 0 would be the first rows. The second row would be negative 4, negative 20, and 24. Once again, it's like you're distributing that 4 to the inside the parentheses. It really is. So it looks like my final answer is going to be what? B? So B is the correct answer for that guy. Okay? And it looks like C, they divided it, right? That's what it looks. C messed up. They divided instead of multiplied by 4. And actually, let's just bring that up. If I want to divide everything by 4, you'd multiply by the scalar 1/4, right? So if you needed to divide, that's what you would do. You wouldn't necessarily put a big division bar and put 4 underneath and put divide by 4, okay? If you're going to do division, you multiply by the scalar of the reciprocal, which would be 1/4, okay? I just want to be very clear with that. All right, so here are some properties of matrix operations. Doesn't matter which way I add the matrices, they're still going to be the same, and that makes sense because they have to be the same dimensions. So if they're the same dimensions, nothing's really changing. The associative property works. Doesn't matter which way I group the matrices, I'm still going to get the same response. Left and right scalar distribution. If I multiply from the left, it's the same if I multiply by the right. Only with a scalar. Only if it's a number. Notice, I do not have anything up here if I multiply 2 matrices together. So for instance, you're not seeing this yet. I'm not talking about this yet. That's a whole entire lesson, okay? Multiplying two matrices together is a little bit trickier, and we have some rules for that, okay? But when it comes to multiplying by one number, a scalar, it doesn't matter if it's in the left side of the matrix or the right side, you're still going to get the same response, okay? So we're going to try one multi-step problem together, and order of operations still holds. I want to be very clear on that, okay? So we want to find 4a, which is this, and I want to subtract 3b, which is this guy. Okay, I'm going to subtract these two. I'm out of space. I'm pretty sure how I'm recording, you can see the rest of the board, but just in case I can't, I'm going to stay on this side of the board. So my answer is going to be down here, okay? This is a 2 by 2, and this is a 2 by 2. So I'm allowed to do this. If this was a different dimension, I can't do this operation. This guy. So I'm going to, what we could do, in fact, let's do this, we'll do this systematically. The first step would be to multiply each matrix by its own scalar, right? So let's do that. So this guy, multiply 4 to everything. I get 8, -4, 12, and 0. This guy, I'm going to multiply 3 to everyone, so I get -6, 0, 3, and -3. Okay? Now, I'm going to subtract these guys to get an answer. So 8 minus a -6 would be 14. I'm going to add them, so just be careful with negatives. 12 minus 3 is 9. -4 minus 0 is -4. 0 minus a -3 becomes +3. So here's my answer for that guy. Okay? Now, could you do this in one step? 4 times 2 is 8 minus a -6, which is adding it, gives me 14. Yes. The more steps you put in your mind, the more susceptible to a minor math error you are. Okay? Boy, that sounded, could that sound like Yoda? Maybe it sounds like Yoda, I don't know. You know, I'm not going to do a Yoda voice. No, I'm not doing that. But I would do the distribution first, the multiplication by the scalar, and then subtract them out. If you want to, you can multiply this whole thing by a -3, which would change the signs, and then put a plus sign there. You could make it an addition problem if you like. Okay, that's definitely an option. So I'm going to do one word problem to wrap things up. Okay, and we're just going to work on these operations for the next couple days just to get used to it, do some word problems with it, and then we'll jump into multiplying by matrices for our next lesson. So it says here, a business, a small company, makes unfinished desks and cabinets. Well, that's cruel. I hate putting together stuff. Each item requires different amounts of hardware as shown below. So for the desk, here's its matrix. Nails, there's 10 short, 6 long. For screws, there's 8 short, 4 long. For a cabinet, we have 4 short nails, 8 long nails, 3 short screws, 4 long screws. See how the matrix works with that? The company has orders for 3 desks and 4 cabinets. Express the company's total need for the hardware in a single matrix. So I want to combine that all into one. So here's the deal. I'm going to have 3 of these matrices put together, 4 of these guys put together, and then I'm going to add the finished product, and that matrix will tell me the totals I need to send to that order, that customer. Okay, so that has everything. So if this was set up in a computer, okay, the computer will be able to go through this rather quickly. So here's what I'm going to do. I need 3 orders of the desks plus 4 orders of the cabinets, and that's going to give me my total. So now what I'm going to do is I'm going to write this matrix out. So 3 times this matrix plus 4 times this matrix. Okay? Now notice they're both 2 by 2s, so that's important. And based on context, these guys are the same thing, right? Don't both these represent short nails? These represent the longer nails, and the screws do the same thing. See how dimensions are very important when it comes to matrices? When it comes to context, it's even more important, okay? So what I'm going to do is I'm going to multiply this by 3 first. So I get 30, 24, 18, and 12. For this guy, I'm going to multiply everything by 4. So 16, 12, 24, and 16. I'm running out of space here, guys, so I can't put a matrix there. So far, so good. Now we add the final result. So 30 and 16 are both in the 1, 1 position, so I get 46. Okay, 18 and 24 would give me what, 42? 24 and 12 gives me 36. 12 and 16 gives me 28. Okay, so here are my totals for that order. Okay, so this is for the order that we have. All right. Now, let's interpret it. So this position is telling me I need, what, 46 short nails, and I need 42 long nails. This one's saying I need 36 short screws and 28 long screws. Okay, so remember, each position represents something here when we do that. Okay? All right, and to be honest with you, I think I got through everything that I needed to. Yep, I did. My notes online, I do have other examples that I worked out, so if you need some other examples, like I do have another word problem and different things like that, please look at them, okay? If you have any questions, just let me know. But other than that, guys, I think that's it. So, hey, hope you're having a great day, and I will see you guys in the next lesson.